Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, we'll review one of the most important statistical tools that you may ever use, the sample size calculator. We'll talk about and walk through several examples of how to calculate the ideal sample size and the effects the sample size can have on interpreting your data. Please be sure that you've at least reviewed the previous lessons where we talked about population versus sample data, the mean, standard deviation, etc. But for now, let's begin by defining what a sample size calculator is.
Well, a sample size calculator is simply a calculator that helps us determine how much data we need to collect in order to be confident in the results that we're looking for. It's one of the easiest tools I believe I would use and recommend to folks, but most often it's the one that's neglected. And it's a basic tool that could be used for simple data analysis. And if we understood the power behind using a sample size calculator, I think it could make all the difference. So what's the purpose of the sample size calculator? Well, there's several purposes it has. First of all, it could tell us how much confidence or risk there is, the accuracy in a given sample size. Also, it's a way to determine the amount of data necessary in order to sustain a certain level of confidence and accuracy. As well, it also shows the amount of accuracy for a given sample size, as well as the level of confidence or risk level that we might have in a given sample size. So just to show you what the calculator looks like, here's one example. This is the one that I'm going to be showing you and going into more detail about it, but there are lots of other sample size calculators available online. Generally, you're going to see those free. I would never recommend getting one that you have to pay for unless it also does some very powerful things, but for the basic functionality you're looking for, you should be able to find a lot of great free resources for a sample size calculator. Again, this particular one I'm going to show you, this is one that I created that I recommend using, and this is the example of the one that I'm going to go into more detail within this lesson.
Okay, now let's begin to explore the various components of the sample size calculator.
Just before I show you each of the components within this particular sample size calculator, I do want to show you that there's actually two sample size calculators within this one calculator, and each of those has 4 different components. So let's break those down. The first calculator is going to be for discrete data. It's this upper portion here. Now when there's discrete data, this is when it's data that's simply like a yes, no, or true, false, or something that's non-numeric. And then if you have that type of data, that type of discrete value that you're going to be measuring and pulling for your sample, then you're going to use this upper portion of the calculator, the one associated for discrete data. An example also is that if you're trying to do things like for an election, doing a poll to see who's going to win the election, or if you're measuring certain percentages based off of proportions of data, that's the kind of thing that you would see for measuring discrete data for this type of calculator. So the components of this particular calculator include these 4 areas here. That's the defect rate, confidence level, precision, and the sample size, which would also include like the adjusted minimum sample size that we'll get into a little bit later. The other type of calculator is the continuous data calculator, the lower portion here. So this is if you have continuous type of data, or also called variable type of data. Now if your data is like that, then you're going to find yourself using that particular type of calculator for determining the sample size or whatever kind of metric you're looking for. So if you happen to be measuring things like the age of customers, or you're measuring something like call handle time, call duration, or you're measuring the average billing adjustments, like something that's in terms of dollars, those are all continuous type of values. And when you have those types of values that you're going to be analyzing and need and collecting a sample for, then you're going to use this lower calculator that's associated for the continuous data. Now, the components of this particular calculator are the standard deviation, confidence level, precision, and also the sample size. So let's go into each of these different areas and look at the different components so you can see how each of those work. First of all, under the discrete data, you have this one called defect rate. Now, don't let the name fool you for defect rate. It may not exactly be a defect necessarily, but that's the name that's given for this particular variable in this part of calculating the sample size. So what you're going to usually put in here is kind of like the percent of defects that you're expecting. Usually the value cannot exceed 50%. If you try to plug in a value in here that is greater than 50%, then it's going to show up red and be like an error. So you have to have something that is 50% or less. If you don't know what value to put in there, then 50% is the most conservative value. But usually if you know what the value might be, like a percent of defects for example, then that's the percentage. Something that's less than 50%, that's what you can plug in there. So hypothetically, let's say that if you don't know what you're going to be comparing, like if you're doing polling for who's going to win a particular election between 2 candidates. Well, if you have 2 candidates, then there's a 50-50 shot of what a person's going to select between the 2 candidates of who they're going to vote for. So then you put in 50% for them. However, if you're measuring something like the performance for some evaluation of some measurement, and you know the typical performance is about 86%, well then you know that means the defects could be 14%, which is 1 minus the 86%. So in that example, you could plug in 14% like we're happen to illustrate here. And if you know that, but again, if you don't know it, then use 50% as your maximum value, most conservative value. Another way to treat this is you can also use 1 divided by the number of discrete values. So usually when you're doing something that's discrete, you're going to have at least 2 or more things, 2 or more discrete values. I gave the example of doing the elections between 2 different candidates. Well, then you could do 1 divided by 2 because there's 2 possible candidates that somebody can choose from. So 1 divided by 2 is 1/2 or 50%. However, if there are 3 candidates that were running and you're polling people to see who they're going to vote for, you could do 1 divided by 3, which is like 33%. Or 4 candidates, 1 divided by 4, and that's 25%. Then you can plug in 25% here. Now, the lower the percentage that you're going to plug in here, then the smaller sample size that's required. That's why we say to be the most conservative, you probably want to put something like 50% as the maximum value, because that way you're going to get a higher sample size, but also you're being more conservative in case you have something that's wrong. You don't want to underestimate. So it's a good way of ensuring that you're at least getting a minimum number that you might need to sample. The next value in here, next component, is the confidence level. Now this is one that's also the same on both of these different calculators. So for confidence level, this is where you're going to plug in the level of confidence that you want for this data that you're analyzing. Typically it's going to represent the 1 minus your alpha risk, which is also the type 1 error that you might have. Again, it's something that's more familiar with the statistical side of things if you're familiar with the alpha and beta risks. If you know what your risk is, most often, like a default, it might be 5% in many different industries. So if 5% is your alpha risk, then 1 minus that 5% equals 95%, and very often as a default, people will tend to use 95% as a confidence level. So if you're not sure what to use, then I would recommend just using 95%. If you want to reduce your risk even more, your risk of being wrong, then you can increase that to 96, 97, 98, whatever you want. I would not put 100% though. It's not very often that you would see that. You're going to get a much larger sample size, but usually 99% may be the most, or you can use some fraction of that as well. The next component on here is precision. This is also like the margin of error. So if you ever hear of studies where they say this particular candidate has 55% of the votes plus or minus 2%, well, that 2% represents the margin of error. It also represents the precision. How precise is it that you want to have your values? Well, when we're talking about for the discrete calculator here, you're going to use a percentage, and that's the number that you're representing here. Precision is also a component of the continuous data calculator, but in here it's going to be not a percentage, but it's going to be the value for that continuous value that you're measuring. So if you're measuring things in terms of dollars, for example, well, if you want to be as precise as within $10, then you put in 10 if that's your measurement. Or if you're doing it some other numerical value as far as measuring something according to some width or some other scale, then whatever that value is you're using in your scale, that's the value you're going to represent here as a continuous value. So it really depends on how you're representing it between the two calculators, but the premise behind the precision is the same. That is, it represents how precise your data is going to be. It's going to be that margin of error. Next component that's on each of these calculators is the sample size. This is where you're going to be looking for the actual number of samples that need to be collected in order to sustain this level of confidence and also for this level of precision that you've already defined within the calculator. The sample size works the same between both of these calculators, so it's going to give you that result if that's the missing variable that you're looking for. One thing to keep in mind is it says here per lowest level, so you have to be really careful in using the sample size because this is the lowest level number of samples that you need in order to estimate this. So as an example, if you're trying to break down the who's going to be voting for a high-level office across the country, and you might have, let's say, 2 key candidates that are running for office, well, then you might say that you need a certain level of samples in order to know how people are going to vote, or the number of samples you need to collect in order to know how people are going to vote, who's going to be the candidate that seems to have the most votes. Now that might be fine at the top level across the entire country. However, if you're going to break it down between the different, for example, the states or provinces or however you might subdivide the country, now you can't use that same exact sample size. So if it's said in here as a result, you need to collect, let's say for grins here, 4,600 samples in order to measure this for the candidates across the country. Well, that's fine at the country level, But if you wanted to subdivide it between the different states of how each state will be represented, then you're going to have to do something very different. You're going to need at least 4,600 per state. So for each level, and if you happen to have, like in the US, 50 different states, that's 50 different levels. And you'll need to collect at least 4,600 samples for each of those states in order to be confident, again, 95% confident with that same level of precision. So just be very careful in using this. Make sure that the sample size is really the sample size you're using at the lowest possible level of how you're going to subdivide it. So you may want to err on collecting a whole lot more samples if you're expecting that you're going to be subdividing your data in order to do further analysis. Or if you're not going to actually collect more samples, or you can't collect more samples, then just understand you're probably going to have to compromise either your confidence level or your precision in order to account for that subdivided sample size that you've collected. Another value on here is the standard deviation. This is unique to the continuous data calculator. The other one had the defect rate at the top, but the continuous data one has the standard deviation. And it's really easy to calculate. You can use that like in Excel or some simple formula. If you have a long list of your continuous values, you can just use the STDEV function within Excel in order to calculate what is the standard deviation. That's pretty straightforward. And whatever that value is, that's what you can plug in here. Or if you don't know what it is, you can make your best guess to start with, and after you've collected some data, you can adjust it to find out what the true standard deviation should be that you want to represent in here. But that should be an easy one to calculate for you. Again, standard deviation, like we've talked about in other lessons, represents the average distance that each of those observations in your data set are from the mean, or that central tendency, again, assuming that it's a normal distribution. So that's the major components for each of these different calculators. Now, one thing I did not point out yet was the population size. So the population size is one element that's at the top that applies to both of these calculators. Now, the thing with the population size is kind of unique. The population size is really only accounted for when there is a small population, and that might cause the adjusted minimum sample size to be adjusted lower. So where it says sample size per lowest level, right here where it says 4,625, this upper number, that is the most for the most samples that need to be collected in order to maintain a certain level of confidence and a certain level of precision. However, if your population happens to be really small, if it's a much smaller population than this example of 100,000, let's say you have a population of only 4,000. Well, if you have a population of 4,000, you obviously have a lot fewer in your population than the samples you're required to collect. So what this will do is it will adjust downward to something smaller than what your population is to get a reasonable level. Now, it's not going to be much smaller. If you have a population of 4,000, it may drop to something like 3,000 or 3,500 that you need to collect, because generally you don't need to collect the entire population in order to do some statistical analysis. However, when again your population is small like that, you can adjust your minimum sample size to something smaller, and that's what this will calculate for you. But if you get beyond a certain point, for example, in this example here we've got 100,000 noted as our estimated population size, and if you notice, both the sample size and the adjusted minimum sample size are equal in both of these calculators. Well, now I can add extra zeros to this population size. I can instead say if it's 100,000, I can make it 1 million, 10 million, 100 million, or 1 billion, or 1 trillion, it doesn't matter. The greater that I add to this population size is not going to change at all the sample size that's needed to be collected. However, again, if you're going to reduce your population to something smaller, then you may see the adjusted minimum sample size getting smaller, which means you can use that. So you can use, between the two numbers that are available, you can just select whichever one is smaller, and that could be your minimum sample size that you need to collect for that particular data analysis.
Now we'll walk through the steps for using the sample size calculator.
I like this version of the sample size calculator I'm about to show you because there are several extra features that can be used when you're calculating for your sample size and calculating more than just your sample size. So for this particular calculator, let's talk through some of those things. For example, in this particular calculator, you can enter any 3 of the calculator's required components and it will return for you whatever that 4th missing value is. So it makes it a lot easier to work with. For example, for each calculator, again this one that's the discrete one, you'll notice that there are 4 yellow boxes in here. You have to at least enter a defect rate, or in the other one you have to at least enter standard deviation. But if you notice, there are 3 other yellow boxes beneath that. You can enter any 2 of those 3 and it will solve for the missing one. In this example, it's solving for giving you the answer in this answer column, what the sample size is. However, if I knew what the sample size was and I plugged that in here and I wanted to figure out from that what's my precision, then I can leave the precision blank and it will solve for that. Or if I knew what the precision is that I wanted and I want to solve for the confidence level, then again I can delete that, and then it will tell me what the confidence level is for that particular sample size with that level of precision. So it makes it a whole lot easier to work with, where you're not having to go back and forth between multiple calculators, but it's all embedded within this one calculator, and it makes it extremely effective for not only determining the necessary sample size, but also again solving for the confidence level or precision when you have an existing sample size. So again, all you have to do is plug in any one of those values that you have, and whatever the missing value is, it will solve for the unknown value. Now, a note here is that the sample size returns the minimum sample size for lowest levels I had showed on the prior slide. So you got to really be careful that you're only using, you got the right population represented, but you can select the lowest sample size between the sample size and the adjusted minimum sample size, but also you have to make sure that you're using it again at the lowest possible level, depending on how you're going to subdivide your data. So again, if you're going to try to measure things, transactional errors at each of the 100 stores for some measurement that you have, then your sample size should not reflect the total transactions collected across all stores, but your sample should be collected for each store. So you've got to be very careful in how you account for that when you're working with your sample size calculator and planning out how you're going to collect your data for your analysis. So the basic steps you might follow for using this particular calculator is, first we're going to determine what data element it is that you're measuring and the data type. So if you know your data type is discrete, then you're going to determine first of all that you're going to use the discrete calculator. But if it's continuous, then you know you're going to be using the continuous calculator. Next, you want to identify the estimated population size. You're going to plug that in up there once you know that. And then again, based on the data type, which whether it's discrete or whether it's continuous, if it's discrete data, then you want to figure out what is the defect rate. This is the first component within that calculator. Again, as we've talked about before, if you have a metric that's 85%, then 1 minus 85% is 15%. That's the portion that is less than 50%, so that's the portion you can plug in there. Even though it may not actually be a defect itself, so don't let the word defect throw you off. But the fact that the portion is below 50%, that's the lower percentage you're going to represent within here. Or as we mentioned before, you can do 1 divided by the number of discrete values. So if you're polling for 3 candidates, then you could do 1 divided by 3, and you can plug in the value of 33%. Or as a worst case or most conservative level, you can plug in 50%. Now again, if we've got a continuous data that you're working with, then you got to figure out what the standard deviation is. You may need to guess at it first, or again, you can pull a simple calculation, standard deviation, based off of some similar data that you have and use that as a baseline. So the fourth step now we want to do is we want to ask ourselves, how confident are we in the sampled results, or how confident do we want to be? This is like, again, that alpha risk, figuring out the level of risk we're comfortable with, and it's 1 minus that alpha level. Generally, you're going to have, again, the 95% be a default if you know nothing else and you don't have any other defined answer. For some organizations, when there's high risk involved, like with healthcare or with doing some complex engineering, or if you're dealing with some very sophisticated like materials like ammunition or weapons or things like that, you're probably going to have much less risk, and that means you want to increase your confidence level, and that's perfectly okay. But again, if you're not sure what to use, 95% tends to be a good default for most people. And then the last thing we're going to determine is, how precise do you want your data to be in the sample results? Again, this is that margin of error, so that's the next value you want to plug in. And once we've got those values, it's going to solve for the sample size. Obviously, if we already know some of the things, like if we know the sample size, then we can solve for whichever one is missing. But this is the general order you might follow when using this particular calculator.
All right, now let's go through several examples to help demonstrate how to use the sample size calculator.
Well, what I've done is I've split my screen into two, where you can see the calculator on one side with several of the examples we'll walk through together, so you can see how I can apply these situations to the calculator. For the first example, we're going to go through a couple of scenarios, and that example is where we're trying to poll for a local election in a city that has 40,000 people. So in the first scenario, let's see, this situation is, if there are 2 candidates running for local office, how many people should be surveyed of who they'll vote for in order to be 95% confident with plus or minus 3% margin or precision? So this seems pretty straightforward. So first, between the 2 calculators, the first step we want to find out is, which calculator are we going to use? Well, based off of this, we're trying to find out how many people should be surveyed of who they'll vote for. So we know that there are 2 candidates they're going to vote for, and since there are 2 candidates, that's a discrete value. They're going to go for candidate A or B. So in that case, it's going to be the discrete calculator we'll use. Next thing we had was the population, 40,000. So we'll type that in. And then next we were asked several things. We're given like the 95% confidence level, and we're also given the plus or minus 3%. It's our margin or precision, so we'll plug that in as 3%. But we weren't given the defect rate. So since we're not given that at this point, then we can assume maybe 50%, worst case scenario, because people could be voting for one candidate or the other. So I plug 50% in. So now it tells me there's 1,067 people that need to be sampled or surveyed to find out who they'll vote for in order to be at least 95% confident within this plus or minus 3% margin of error. So let's extend this a little bit further. Next situation is, after 300 surveys that have been collected, we're finding that candidate A has 75% of the votes. How does this change the total number to survey? Well, most people might think, well, it doesn't change the survey at all. It shouldn't change anything. We've already determined the number of samples that we need. But I would really beg to differ on that. One approach that I think not many people realize how we can use this calculator is we don't just use the calculator when we're beginning our analysis to plan for the analysis. We should continue to use the calculator all throughout our analysis. That way we can adjust our sample size according to the situation. As the information that you're getting back from your samples changes, then you might find that you need to make some adjustments. So this is the worst case scenario given these parameters of 95% confidence and 3% precision. Worst case scenario, we need to collect 1,067. But now again, after having 300 surveys on our way, got maybe a third, a little bit less than a third of the surveys for the sample, we're seeing that candidate A has 75% of the votes. Well, if that's true, then that means candidate B, the other candidate, has 25% of the votes. Well, now with that information, I can plug in the smaller value, which is 25% in here, and by plugging in the lower defect rate, now it's telling me I only need to survey 800. So now I've reduced my survey significantly. Instead of needing 1,067, I've gone down to 800. Well, this could be a huge savings of time because now I'm still achieving the same level of confidence and the same precision, but now that I have more information to tell me my defect rate is lower, now I can collect fewer samples in order to achieve, again, the same level of precision and confidence. So as you're going through this, don't be afraid to make those kind of adjustments along the way. Now remember, at the same time, if you find after you've collected 800 surveys, if you find it's gone back to be 50-50 between the candidates, then you have to plug your 50% back into this value here again. And by plugging it back in, you'll find you do need to get the full 1,067 as you originally planned. But at the same time, if you find that it just continues to change as far as what that defect rate is, don't be afraid to continue to plug that into the calculator and make your adjustments along the way. Now let's extend the sample a little bit further. What if there were 3 candidates running for office? How does that change things? Well, if there are 3 candidates for office, what we said was candidate A has 75% of the votes. Well, if there were 3 candidates for office at the very beginning, we could do 1 divided by 3 as 3 discrete values and plug in 33%. But again, after getting 300 surveys, we said candidate A has 75% of the votes. Well, let's assume too then that means candidates B and C, the other 2 candidates, have a split value of the remaining votes, the remaining 25%. Well, if they have a split value, that is candidate A is 75%, the other 2 remaining candidates have an equal share of the 25%, then that means each of those other 2 candidates actually have 12.5%. So now I can plug in 12.5% here, and it reduces my sample size even more. Now, what this is doing is it's just telling me how many samples I need to collect in order to have 95% confidence with this level of precision that one or more of my discrete values is different than the others. In this example, we're saying candidate A has 75% of the votes. So I only need 467 samples in order to prove that candidate A is the far leader and very different from the other group. This information, these number of samples, will not tell me between the other 2 remaining candidates, candidates B and C. It won't tell me who's leading between them necessarily unless they have a clear difference between them, like one is 1% and the other one has 24%. Well, I might be able to determine from there between them, but if they have an equal share between candidates B and C, this amount of surveys is not going to tell me that. All it's going to tell me is that at least one value among all those discrete values that I'm evaluating, at least one of those values is clearly different than the others. And that's what we're saying, that candidate A is going to be the winner because they have 75% of the votes. Now let's adjust this a little bit further. Let's say that for this example, the city had only 12,000 people and we wanted to have 1% precision. Well, how is that going to change our sample size? Well, if we know that we want to reduce this down to 1% precision when we want to be more precise, but we're finding that the population size is really only 12,000 people in the smaller city, you can see the adjustment it's going to make is I've got 4,202 that I should be sampling, but because of the smaller population, it's saying that I really only need to collect 3,112 in order to still achieve this confidence level and precision for this smaller population. So this is where in this example you'd probably want to use the smaller one. You can use the higher one if you want to, but it's not as required since your population is much smaller. But if there's a chance that you might have miscalculated your population and it is much bigger, then just be aware you probably need to make some adjustments to that, and it will increase your adjusted minimum sample size too. So just be aware of that, but it's okay. Normally if you know your population size is smaller, it's okay if you wanted to use the smaller adjusted minimum sample size instead. Alright, now let's extend this situation to scenario 2. Let's say that there are 4 candidates running for local office. How many people should be surveyed to find the age of the average voter and be 95% confident with plus or minus 1 year? Well, in order to figure this out, we have to first again figure out which calculator we're going to use, the discrete or continuous. Well, we're not really trying to measure who's going to vote for who, so it's not really discrete values in the again. What we're trying to figure out is how many people should be surveyed to find the age of the average voter. So age is what we're looking for. Age is a continuous value. You can argue to some degree that it's discrete because there aren't going to be people that go on into infinity necessarily, and we know the bottom value is going to be the bottom level, like 18 or 21, whatever that voting age for that local area. So you know you're going to have some limitations there, and in some way you can argue that's discrete, but for this example, let's just presume it to be continuous. So we'll use the continuous data calculator to figure out what that age is in order to get enough surveys to figure out what the average age is. So in this example, we know again we want to use 95% confidence, and we want to do it within plus or minus 1 year. So we've got the 1 plug in there because we said 1 year since we're looking for an age. So we're using the same level of calculation to represent here. It's 1 year. So for this, we might have to make some guesses as far as what the standard deviation is. We may not have any data yet. So without knowing much else, let's just arbitrarily say maybe it's 8 years as our standard deviation. Well, if that's the case, then it's saying that we need to collect 246 samples in order to figure out what the average age should be for those people that we're surveying. But let's say actually we were surveying a lot more people and we got 300 surveys, and we found that based off of some other data we collected, the average age for people was 42 from a prior analysis, but the standard deviation was 12. Well, we'd have to plug in here 12. Again, the factors that we've added in here, that there are 4 candidates, really doesn't mean anything. The fact that we've identified the average age here really doesn't mean anything. It's nothing that we need to plug in. So it's extra information that's just not necessary for this calculation. But the standard deviation is important for us. So we plug in 12 years there as the standard deviation, and now it tells us our sample size we need to collect is 553 instead. So let's extend this a little bit further. What if we could only survey 400 people and not the full 553? How does that affect your confidence level and your precision? Well, if we know we can really only use enough resources to collect 400 samples, that's the most we can collect, or maybe within a certain time constraint we might have. So then really what we're not solving for is a sample size. We know we need more than 400, so we know we have to compromise either our confidence level or our precision. So in that case, we can plug in 400 as our cap, the most samples we know we're going to be able to collect. And now we can solve for precision. So I would delete this value here, and if I only collected 400 surveys, my precision, instead of being within 1 year, now it's only going to be 1.2 years. Or if I wanted to solve for the confidence level, if I want to keep this at 1, I can delete that, and it would tell me, well, with 400 surveys, again at 1 year as my precision, I'm really only going to be 90% confident. So you can see this is how the power of this calculator. You can use the same calculator to solve for whatever that missing value is, so you can figure out where adjustments, some adjustments you might need to make between confidence level and precision. All right, let's go to the next example here. Call duration measurement at a call center. Our scenario is that we want to ask ourselves how many samples are needed to measure each employee's call duration per month with 95% confidence and within 10 seconds of duration. So in this example, what we're trying to measure for is we're trying to figure out, again, how many samples need to be collected, but what we're trying to see is to measure each employee's call duration per month. So call duration, we might say, is measured in seconds. We've already identified that we want to measure it within 10 seconds, so that might be our precision. So So we're going to measure things in seconds, and that's going to be like a numerical value, which is a continuous value. So in this case, we know we're going to use this continuous data calculator. And I know also that my population for the calls that we might have are going to be large. So if I see any adjustments I need to make with my population, I could make this much larger. But in this case, it looks like we don't need to know that, so I'm going to ignore that piece of it for now. But we do know that we want to have 95% confidence. So I'm going to plug in 95% there. And we also know we want to have 10 seconds for our precision. So we're going to plug in 10 there. And we want to solve for the sample size. So we're going to plug that in. But we don't have 12 necessarily as a standard deviation. If we assume maybe a phone call in this area might take 10 minutes, well, 10 minutes would represent about 600 seconds. So maybe in theory, standard deviation could be maybe 150 seconds. So I'll plug in 150. Again, when I don't know what to plug in, I'll use my best guess to determine it, and after I collect some data, then I can make adjustments. So in this case, let's say we used 150 seconds. Now it's telling me 864 is the number of samples I have. Now, as I mentioned before, I see it's got an adjusted minimum sample size. So if I did have 12,000, which was from my previous example, if I only had 12,000 calls per month as my population, then this might be necessary. However, if I'm handling a lot more calls than that, for example, like 20,000 calls per month, then you can see it's increasing, and now both of these are the same. So now I know I need to collect 864 samples in order to figure out what the each employee's call duration would be per month. Now, what if we only had 300 samples per employee? It's telling me I need to collect 864, and again, I want to get down to each employee's call duration. So at this, let's just say I only have 300 samples per employee to collect from, and how's that going to affect things? Well, again, if we got that constraint, then we might have to plug in 300 as the max, but now we might need to either adjust our precision, so I'll delete that, and now instead of being plus or minus 10 seconds, I'll really only be plus or minus 17 seconds. Or if I wanted to keep it at 10 seconds, now I can delete the confidence level. Now I'm only going to be 75% confident, which means it gives me a 25% risk of being wrong. So this is where, again, with the constraints that we might have, we might need to make some adjustments in how we're going to evaluate this, whether we're going to have to compromise the confidence level or compromise our precision, but at least we're aware of the risks we're taking. And understanding how this calculator works will make us aware of that, so that way we can make sure we're making the most informed decision. And again, after you collect some data, you might find you can reduce this standard deviation. If you can reduce it, for example, down to 100 seconds, because maybe you have a much more consistent process for the agents while they're on the calls, well then, just by reducing the standard deviation can make a huge improvement to the confidence level. Or if I plug my 95% back in here and solve for the precision, now instead of being 17 seconds, I'm down to 11.3 seconds of precision, which is much closer to the 10 seconds that I desired. So these are, again, ways that you can kind of figure out where you need to compromise if you have some certain constraints given on you in your situation. Let's move on to the last example here. We're trying to compare the efficiency between two different systems. And let's say that you've got 90 similar transactions you collected from each system, and you're trying to see which one's faster. For system alpha, the time was 45 seconds. And for system beta, their time for processing the transaction was 27 seconds. Let's assume they had a standard deviation about 1/3 of the total number of seconds, or these average seconds for each system. So in this case, is system beta statistically faster? Well, when we're using just the average, it sure looks like it's faster, but we know we only have 90 transactions we're looking at, so we're not really sure. Well, in this case, what we're trying to measure is seconds again, and this is going to be a continuous value, so we know we're going to use this continuous calculator for this example. We have 90 transactions we're working with, so that's our sample that we have for each system. So we're going to plug in 90, so that's what we have for each one. Again, that means we have 180 total samples, but in this case, we've only collected 90 for each one, so we're going to plug in 90 per each of those different systems. And for the first system, they were at 45 seconds, and system beta, they were 27 seconds, and we said 1/3 of that was their standard deviation. So if we're first going to solve for, in this case, we're going to solve for precision. How precise are we with each of these? And we know we're going to assume like a 95% confidence on them. So in this example, what we're going to do is we're going to plug in the standard deviation for the first system, where it's 1/3 of 45 seconds, so that would be 15 seconds. I plug in 15, their precision is 3.1 seconds. So to help figure this out, I'm going to plug in some values in here. I'm going to plug in high, average, and low. I'm going to say this is for system alpha, and this is for system beta. So we're going to compare the two systems. So in the average, we said for system alpha, theirs was 45 seconds. Let me center each of these to make it a little easier for viewing. And for system beta, theirs was 27 seconds. So what we're going to do is we're trying to solve for what the true range is for both systems, and this is where the precision really helps us. So given the standard deviation and the number of samples that we have with 95% confidence level, we've determined on here 3.1 seconds is the number of the number of seconds for the system alpha. So we're going to add in here equals this plus 3.1. And for the low end, we're going to do, again, this minus 3.1. Now it tells us for system alpha, their average is about 45 seconds, but the true range could be anywhere from 41.9 seconds up to 48.1 seconds. That's their true range, or what we're calling kind of like our confidence interval. Now for the beta system, we're doing the same thing, but at theirs, they had 27 seconds, and again, standard deviation was a third, so that would be 9 seconds, so we'll plug in 9. So now for them, the precision is 1.9. So up here, we're going to do equals this cell plus 1.9, and do underneath equals that same cell minus 1.9. So now for system beta, their actual performance is somewhere between 25.1 seconds and 28.9 seconds. So what we're factoring here is what's the best worst case difference in efficiency for system beta. Well, for system beta, their best case their best case is 25.1, but their worst at their slowest is probably for the average going to be about 28.9. Well, the best that system alpha can hope for is 41.9. The fact that these are so different from each other, between the 28.9 for system beta, their worst case, and alpha's 41.9, which is their best case, the fact that there's a big gap between those tells me that system beta is actually statistically faster, because in the worst day for beta and the best day for alpha, they're probably still going to be performing where beta is much faster. So this would give me that confidence in knowing that the difference in the performance between both systems. Now let's adjust this a little bit more. Let's say we only had 24 samples to look at, so that's going to adjust this number of samples. And let's say that system alpha was actually 180 seconds and system beta was 160 seconds. We'll use the same standard deviation being a third, so for system alpha, for them, 180 seconds, a third of that is 60. So plug that in, that's 24 seconds. So we'll plug in instead here for the average for them was 180 seconds. We're going to add to that 24 and subtract from that 24, because 24 seconds is the precision for system alpha. So the average performance is 180, but the true average is going to fall somewhere between 156 and 204, so it's a pretty wide range. For system beta, their average is at 160 seconds. And if they are 160 seconds, we're going to say equals 160 divided by 3. Then 53.3 is their standard deviation, and their precision is 21.3. So for them, we're going to add 21.3, and then for their worst case, 21.3, or best case it is. Now for these two, what we're seeing is for alpha, the fastest alpha will probably perform at least on the average, what their true average might be for the true population of all the transactions. Their true average could be as low as 156 seconds. For beta, their true average could be as high as 181.3 seconds. Well, if you notice, there's a big overlap now between them. 156 seconds is much lower than the 181 seconds for the system beta. So now when I compare the two, it still might look like system beta on the average is faster because they showed 20 seconds faster on their average for the 24 samples we had. However, because there's a lot fewer samples and because we also have less precision in this, it's a lot harder for us to say that there's a difference, that beta system is actually performing much faster than system alpha. And this is the kind of thing that can help determine this. And actually some statistical tests that calculate based off of confidence intervals will tell us the same kind of thing. But what I'm trying to illustrate here is just how you can compare them and plug these numbers manually like this if you want to see the performance differences using this precision value. The precision value is very critical in how we understand it because it can make all the difference when we're trying to compare things. We should not just compare things between their averages. We need to understand, based off of the samples we collected and based off of these other factors like our confidence level and like this input of a standard deviation, we need to figure out from those the difference that it can make in our precision. and understanding the difference in the precision can make all the difference in determining is system beta really that much better. Well, according to this analysis, we can't say statistically it is. There's not enough data to prove system beta is faster. Maybe it really is, but all this is telling us is that we need to collect more data to really prove that out if that's truly the case. Our first example, it was the case. We had enough data to prove that. The second example, we didn't. So this at least would give us more information to know we have to go back, get more samples, or just make sure we're getting a better perception of the performance of the system.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to identify at least two different metrics that you use in your organization that are using some sort of sample data. For example, it could be surveys, or it could be some other proportion sampling that's done on some evaluations, or QA group that's doing some evaluations too, and they're just using some samples, those kinds of things. And for each of those different metrics that you're looking at, try to ask these few questions. For example, what's the ideal sample size for each of those different metrics in order to have 95% confidence? Now, you need to use the existing metric to determine the ideal precision typically used, and also you'll need to figure out, based off of the existing metric, the defect rate or the standard deviation, depending on which calculator you're using, the discrete calculator or the continuous calculator. And how does this answer compare to the actual sample size that's used for that particular metric? If the organization doesn't meet the ideal sample size that you calculated, then what effect does that have on the confidence level or on the precision for each of those metrics? Next, I want you to try to determine how the organization typically applies rational subgrouping for each of those different metrics. How many levels exist for each type of those subgroups? And does the organization have at least the ideal sample size calculated for each of those different subgroup levels? If they don't, then what's the effect that has on the confidence level or in the precision of that metric?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.